Question number 1, that is 238U92 emits 8 alpha particles and 6 beta particles. The neutron to proton ratio in the product nucleus is. The question asked in EAMS 2005. First of all, in alpha decay, let us assume that is X nucleus, that is your parent's nucleus, XAZ. Z is nothing but atomic number, that is number of proton, and A is nothing but nucleon, number of nucleon or atomic mass number. So in alpha decay, the atomic mass number A is decreased by 4 and Z, that is the atomic number or number of proton, is reduced by 2. That means it becomes A minus 4, Y, Z minus 2. That is called as the daughter nucleus. Similarly, in beta minus negative beta decay process, the atomic mass number remains same, but the Z, that is the atomic number or number of proton, is reduced. It is increased by plus 1. That means in negative beta decay, A remains same in daughter nucleus, but Z is increased by plus 1. So here 8 alpha particle. After 8 alpha emission, what happened? That is U23892, the X in daughter nucleus, it becomes 206X76 because A is reduced by 32, and similarly Z is reduced by 16 because here in alpha process, what is alpha emission? That is your atomic mass number, that is A is decreased by or reduced by 4. That means the total 8 into 4, that is 32. So 238 minus 32 after 8 alpha emission. So atomic mass number or the number of nucleons A remains 206, and similarly that your atomic number Z, that is decreased by 16 after 8 alpha emission. So 92 minus 16, it becomes 76. So atomic mass number or number of proton remains 76. So that is your after 8 alpha emission, that is the daughter nucleus, that is 206X76. Now in case of beta negative beta decay, that is your 6 beta. After 6 beta decay, what happened? That your atomic mass number A remains same, but that your atomic number or number of proton, that is increased by plus 6. So 76 plus 6, it becomes 82. So after 8 alpha and 6 beta decay, that your daughter nucleus, that is Y 20682. So number of neutrons is nothing but A minus Z. That means 206 is your total nucleons or atomic mass number, minus 82 is your number of protons. So it becomes 124 and number of proton is 82. So the N to P ratio, the number of neutron to proton ratio, is 124 divided by 82. So it becomes 62 divided by 41. So the option C is correct. Next question, in the reaction given, that is 2H1 plus 3H1, it gives the reactant 4He2, that is the helium, plus 1 neutron is liberated. If the binding energy of 2H1, 3H1 and 4He2 are respectively A, B, C in mega electron volt, then the energy in mega electron volt release during this reaction is what? So we have to find out the energy release during this fusion process. That is your binding energy of 2H1 is A, that is your binding energy of 3H1 is B, and 4He2, that is your reactant, that is given is C. So first of all, we have to find out the energy release. The formula of energy release is nothing but according to Einstein relation, that is E is equal to delta mc square. What is delta m? Delta m is nothing but mass defect. Mass defect is equal to mass of product minus mass of reactant. Here the mass of product is C and mass of reactant is A plus B. So C minus A minus B, that is your mass defect. Now E is equal to delta mc square, energy release is equal to delta mc square, E is equal to. So 1 AMU, 1 atomic mass unit, is equal to 931 mega electron volt. So what is E? E is equal to delta m, that is mass defect, into 931 MeV, that is mega electron volt. So basically in place of delta m, we put here E is equal to C minus A minus B, because C is nothing but mass of product and minus A plus B is nothing but mass of reactant, and 1 atomic unit is equivalent to 931 mega electron volt. So our answer is C minus A. Question number 3, in a radioactive material, the activity at time T1 is R1, later time T2, the radioactivity becomes R2. So if the decay constant of the material is lambda, that is nothing but a disintegration constant, then which of the following option is correct? So what is the decay rate? R is proportional to minus dN by dt, that is nothing but the decay rate R of the radioactive material is the number of decay per second. That means minus dN by dt is proportional to N and minus dN by dt is again proportional to R. So you can say that the decay rate R is equal to minus dN by dt, and minus dN by dt is equal to lambda into n, where n is nothing but the number of active nuclei after t second. That means the number of active nuclei left after t second. So R is equal to lambda into n. In place of n, we write here n naught into e raised to minus lambda into t. N naught is nothing but the number of active nuclei at t equal to 0, initial time. So that's why in place of n, we write here n naught e raised to minus lambda into t. Based on this formula, you can say that R naught is equal to lambda n naught, where is the activity of radioactive material at t equal to 0 time. Initially R naught is equal to lambda into n naught. That means at time t1, R1 is equal to lambda, that is your R1 is equal to R naught e raised to minus lambda t1, and at time t2, R2 is equal to R naught e raised to minus lambda t2. So if you take the ratio of R1 by R2, that is e raised to minus lambda t1 divided by e raised to minus lambda into t2. So after simplify this, is equal to e raised to minus lambda is common, t1 minus t2 in bracket. So R1 is equal to R2 e raised to minus lambda t1 minus t2. That is your option number A is correct. Question number 4, that the fission of nuclei is possible because the binding energy per nucleon in them, that is the graph of binding energy per nucleon. That means nucleon is nothing but the number of proton plus neutron, that is in the nucleus. So binding energy per nucleon is given in mega electron volt per nucleon, and on the x-axis, that is your nucleon number, that is your atomic mass number, or proton plus neutron, that is represented on x-axis, and on y-axis it is the binding energy per nucleon. See the graph. First it is slightly increasing, then in between, after we increase, as we increase the atomic mass number, the curve is decreases. That means if you increases the atomic mass number or nucleon number, what happen? The fission leads. That fission leads to decrease in the mass number. The decrease in mass number will increase the stability of nuclei. So if you reduce the mass number, that means your atomic mass number that will decreases, that will increase the stability of nuclei and making the fission of nuclei possible for heavy nuclei. Binding energy per nucleon decreases as the atomic mass number is increased. See here, the binding energy per nucleon, this graph is decreases as we increase the atomic mass number. So here the binding energy per nucleon is decreases, that is your binding energy per nucleon is decreases as we increase the atomic mass number. So that's why the fission of nuclei is possible, because the binding energy per nucleon, that is represented on y-axis, that is decreases. The binding energy per nucleon, that is in mega electron volt per nucleon, that is decreases with the increase in mass number or atomic mass number, that is your A. As your A is increased on x-axis, that your binding energy per nucleon tends to be decreases. So option C is correct. Question number 5, which one of the following is possible nuclear reaction? That is 4 nuclear reaction process is given, out of which one of the possible nuclear reaction we have to identify. So option B, see this, in option B it satisfies. First of all, we have to satisfy the conservation of atomic mass number as well as atomic number. That means the number of proton and the number of atomic mass number or the number of nucleon remains same on the both side, that is product and reactant side. So option number B, that is your 23Na11 plus 1H1, that will give 20Ne10 plus 4He2, that it satisfies both the conservation of charge as well as mass, but it is not possible nuclear fission reaction process. So it satisfied the mass of conservation, and also it follow the principle of conservation of charge, because here is total number of atomic mass number is 24, here is also atomic mass number of or nucleon is 24 on the reactant side, as well as on the left side the number of proton 11 plus 1 is 12, and here is also 10 plus 2 is 12, but it is not a possible nuclear reaction process. The option number C, which is the correct answer for this question, that is 239 Np 93, that will give 239 Pu 94 plus beta minus, that is negative beta decay, and V bar is nothing but anti-neutrino. See here, that is 239, that is your atomic mass number A, here is also 239, beta minus and anti-neutrino, beta having charge equal to -1. It is atomic mass number of beta is 0, but the charge on beta is equal to -1, and antineutrino are chargeless as well as having 0 rest mass. So you can say that antineutrino are chargeless, there is no charge present on antineutrino and 0 rest mass. So in order to balance or in order to satisfy the conservation of mass and charge, that atomic mass number A is on the left side is 239, here is also 239, because beta and antineutrino it is 0 -1, here is 0 0. So you can say basically that is your atomic mass number A remains same on the both side, as well as charge. The charge here on the left side is 93, that is the number of atomic number of proton that is on the left side is 93, and here is 94, and beta having -1 charge, so 94 -1, and antineutrino is chargeless, so that's why it is 0, it becomes 93, that is 93 is also on the reactant side, or you can say that your this process is satisfy both the conservation of charge as well as conservation of mass number. That's why option C is correct. Now question number 6. A radioactive material has a half-life T-half of 10 days. What fraction of material would remain after 30 days? That means the radioactive material has a half-life of 10 days. T1/2 is given 10 days, and the time taken for this half-life is nothing but T equal to 30 days. Now we have to find out after 30 days what fraction of material would remain. That means the fraction of material would remain, that means n by n naught. N is nothing but the number of active nuclei remains after T second, and n naught is nothing but number of active nuclei or number of undecayed nuclei remain at T equal to 0 time. That means initially the number of active nuclei is n naught, and after T time the number of active or undecayed nuclei remain in the nucleus is n. So you can say the half-life is given T half is equal to that is 10 days, and it after 30 days of time interval, what is the fraction of nuclei n by n naught? We have to find out this. So first of all you can say that number of half-life is equal to time divided by half-life, that is n is equal to number of half-life is equal to 30 days time divided by half-life, that is 10 days. So the number of half-life is equal to 3. Now based on this formula, number of undecayed or active nuclei remain after n half cycle or n half-life. The number of undecayed or active nuclei remain after n half-life, that is n is equal to n naught 1 by 2 raised to n, that is n is equal to n naught 1 by 2. What is n? In place of n we write here 3, that is based on the number of the time taken for this half-life divided by half-life, that is T1/2, that is given 10 days, and 30 is your time. So that is nothing but n by n naught, the fraction of nuclei n by n naught is nothing but 1 by 2 whole raised to q. So n by n naught is equal to 1 by 8, and 1 by 8 is nothing but 0.125, that is after 30 days the fraction of material remain is 0.125. n by n naught is the ratio, that is the answer is 0.125. Question number 7. In any fission process, the ratio of mass of fusion product to that of mass of parent nucleus is, that is less than 1, greater than 1, equal to 1, or depends on the mass of parent nucleus. In fission process, when a parent nucleus breaks into daughter nucleus, then some mass is lost in the form of energy. That's why the mass of fission product is always less than the mass of parent nucleus. Here the denominator is more than that of the numerator. The mass of parent nucleus, that is always more than that of the mass of fission product. That's why the ratio is always less than 1. That is that for example 235U92, that is your parent nucleus, that is breaks into beryllium and krypton, that is your fission nucleus, or that is your daughter nucleus. So the mass of daughter nucleus, that is 56 and 36, that is individually very less as compared to the mass of parent nucleus. That's why the mass of fission product is always less than the mass of parent nucleus. So the ratio of mass of fission product to mass of parent nucleus is less than 1. So answer is C. That question number 8. The fossil bond has C14 carbon 14 to C12 ratio, which is 1/16 of that living animal born. If the half-life of C14 is 5730 years, then the age of fossil born is what? The half-life is given, that is T1 half, that is for C14 is 5730 year, that is given in a data. Now from the equation of n by n naught, that is the ratio of C14 to carbon C12 is given as n by n naught is equal to 1/16, where n represent the number of active or undecayed nuclei after t time, and n naught represent the number of active nuclei at t equal to 0 initially. So n by n naught is equal to 1/16, that means n by n naught is equal to 1/2 whole raised to 4, and n by n naught is 1/2 whole raised to n. If we equate these two equations, then the power becomes n is equal to 4, where n is nothing but the number of half cycle equal to time t divided by half life T1 half. So your number of half cycle is equal to 4. Now from the above formula, that n is equal to t time divided by T1 half, that is your half life, that the time is equal to that half life into number of half cycle. The number of half cycle is 4 and the half life is given as 5730 years. So it becomes the total time is nothing but 22,920 years. That is the total time of age of fossil born. Option number C is correct. Question number 9. The binding energy of deuteron is 2.2 mega electron volt and that of He42, that is 28 mega electron volt. If the two deuterons are fused to form one single helium nucleus, then the energy release is, in a nuclear fission process, the two deuteron combines to form one He, that is 2 He4. The atomic mass number of He, that is 4, A is equal to 4, and Z represent 2, that is the atomic number or number of proton is equal to 2. And energy release, the energy release during this fusion process or reaction is the difference between the binding energy of daughter nuclei and that of the parent nuclei. So simply the energy release during this fusion process is the binding energy of helium 2 He4 minus binding energy of 2 deuteron, that is 1 H2. So the binding energy of helium 2 He4 is given as 28 mega electron volt, and binding energy of 2 deuteron is nothing but 2 into 2.2, that is 28 minus 4.4, so it becomes 23.6 mega electron volt, that is the energy release during this fusion process. So option number B is correct. Question number 10. The two radioactive material X1 and X2 have the decay constant phi lambda and lambda respectively. If initially they have the same number of nuclei, then the ratio of number of nuclei of X1 to that of X2 will be 1/E after time. So we have to find out the number of nuclei X1 to X2, the ratio of number of nuclei. From the radioactivity equation, n is equal to n naught e raised to minus lambda t, that is for X1 nucleus, that is X1 is equal to n naught e raised to minus phi lambda t, because time constant for X1 nucleus is 5, and X2 is equal to n naught e raised to minus lambda t, the time constant for X2 nucleus is 1. So if you take the ratio of number of nuclei X1 to X2, that it becomes n naught e raised to minus phi lambda t to that of the n naught e raised to minus lambda t. So n naught cancel out each other. X1 upon X2 is given as 1/E. So 1/E is equal to minus e raised to minus phi lambda t, exponential as minus phi lambda t plus lambda t. After simplification, e has power minus 1 and e has power minus 1 is equal to e raised to minus 4 lambda t. So 4 lambda t is equal to 1. So t is equal to 1/4 lambda. That is your time or the number of nuclei to that of X1 to that of X2. The ratio of X1 to X2 will be 1/E when time t is equal to 1/4 lambda. The ratio becomes 1/E when your time is equal to 1/4 lambda. That option number C is correct. Question number 11. If the radius of 13 aluminum 27 nucleus is estimated to be 3.6 Fermi, then the radius of 52 tellurium 125 nucleus nearly. That is, radius of nucleus is directly proportional to atomic mass number has power 1/3 a raised to 1/3. For aluminum, the atomic mass number, or you can say that your number of nucleon A is equal to 27, and R aluminum is proportional to A has power 1/3. So R aluminum is directly proportional to, that is, A has power 1/3. So R aluminum is equal to K times A has power 1/3, where K is nothing but the proportionality constant. RAL is equal to the radius of aluminum is equal to K times 27 has power 1/3, because A is given in case of aluminum, that is atomic mass number is equal to 27. So 27 has a power 1/3, it becomes 3K. So radius of aluminum is already given, that is 3.6 Fermi meter. R aluminum is equal to 3K, that is your equation number 1. For tellurium, that is 125 is your atomic mass number. So based on this formula, that radius of tellurium is proportional to A has power 1/3, that means 125 has power 1/3. So R tellurium is equal to K times 125 has power 1/3, that is nothing but 5K. So R tellurium, radius of tellurium is equal to 5K. So now dividing equation 2 by 1, that R tellurium, radius of tellurium divided by radius of aluminum is equal to 5K by 3K. So R tellurium is equal to 5 by 3 into 3.6. After simplify these, the radius of tellurium is nothing but 6 Fermi-meter. So option number A is correct. Question number 12, that the mass of lithium-7 3 nucleus is 0.042 AMU. That is nothing but a mass defect that is given in 0.042 AMU, less than the sum of masses of its nucleons. Find the binding energy per nucleon. First of all, the mass defect that is given delta M, that is 0.042 AMU or 1U, that is 1U or 1 AMU equivalent to 931 mega electron volt per C square. So first of all, the mass defect has been converted into that your mega electron volt per C square. So we have to multiply 0.042 by 931 mega electron volt per C square. So mass defect becomes 939.1 mega electron volt per C square. After converting these, finding out the binding energy based on the formula E equal to delta MC square. Delta M, the mass defect represented now, that is 39.1 mega electron volt per C square into C square. So binding energy is nothing but 39.1 mega electron volt. Now in question they asked the binding energy per nucleon. So binding energy is 39.1 mega electron volt, that is in mega electron volt divided by the number of nucleon, that is given here. A is equal to 7, the number of nucleon. So 39.1 divided by 7, it will give 5.6 mega electron volt energy per nucleon. That is your binding energy per nucleon. So B option is correct. Question number 13, in a following nuclear procedure, identify the correct sequence that of alpha, beta and gamma decay. The particle emitted in the sequence, which of the following is the correct sequence? So that is your X A Z, that is becomes Y A Z plus 1, then it becomes A minus 4 B star Z minus 1, then it becomes A minus 4 B Z minus 1. So in beta decay, atomic mass number remains same, but the atomic number is increased by plus 1. See here, in first procedure, X is represented your parent nuclei and Y represented your daughter nuclei. The atomic mass number in case of beta decay is remains same, but the number of proton is increased by plus 1, or number of that atomic number is increased by plus 1, so it represents a beta decay. In the next procedure, the atomic mass number or number of nucleon is reduced by 4 and number of proton or Z plus 1 is reduced by Z minus 1. That means it is decreased by minus 2, so it becomes Z minus 1. So that is your alpha decay. It represents alpha decay. And the third procedure, in a gamma decay, that your number of nucleon and the number of proton A and Z remains same. See here. So that the third and last procedure is your gamma decay, where both A and Z remain same, it consisting of electromagnetic radiation. So the correct sequence for these it is beta, alpha and gamma. So option number B is correct. Question number 14, for a radioactive material half-life is 10 minutes. If initially there are 600 number of nuclei, then the time taken in minute for the disintegration of 450 nuclei is. Here in data, half-life is given, that is T1 half is equal to 10 minutes. According to the formula of T1 half half-life, that is ln by 2 upon lambda, where lambda is the disintegration or decay constant, that is ln2 has a value of 0.693 divided by lambda. Lambda is equal to 0.693 upon 10 minutes. If you subjecting the lambda, then T1 half is given, that is 10 minutes. So lambda is equal to 0.693 upon 10, that means 0.0693. That is the disintegration constant. Now number of nuclei T equal to 0. Initially the number of nuclei is N naught, that we denote as a N naught, that is 600. And the number of nuclei disintegrated, that is 450. The number of nuclei disintegrated or decay, that is 450. So total number of active nuclei, or which is undecayed. So number of active nuclei or the nuclei left undecayed, that is N is equal to 600 minus 450, because initially there are 600 nuclei and then 450 disintegrated. So number of nuclei left undecayed or active nuclei, that is nothing but active nuclei. So n is equal to 600 minus 450. So it comes out to be 150. Now according to formula of Rutherford-Soddy law, that n equal to n naught e raised to minus lambda into t. So n by n naught is equal to e raised to exponential as a power minus ln by 10 into t. That is ln by 10 is nothing but 0.0693 t. That exponential as a power, negative power, that is minus 0.0693 t, and n is equal to 150, that is active nuclei, and n naught is initially present, that is 600. So 150 by 600, that comes out to be 1 upon 4. E has a power, exponential has a power minus 0.0693. Now taking the antilog on both sides, that ln 1 by 4 is equal to minus 0.0693. In order to remove this exponential, we have to take antilog. So ln 1 by 4 has a value of negative minus 1.386 is equal to minus 0.0693 t. Now in order to find out time t, t is equal to 1.386 divided by 0.0693. So it comes out to be the time for disintegrated of 450 nucleus or 450 nuclei. The disintegration, the time taken for disintegration of 450 nuclei, t is equal to, that is 20 minutes. Option number B is correct. Question number 15. A nucleus of uranium decays at a rate into nuclei of thorium and helium. Then 4 options are given. The helium nucleus has less kinetic energy as compared to thorium nucleus. Helium nucleus has a more kinetic energy than thorium nucleus. Helium nucleus has a less momentum than thorium nucleus, or helium nucleus has a more momentum than thorium nucleus. 4 options are given. So since there is no external force acting on a uranium nucleus, momentum will be conserved. So P initial of uranium nucleus, that is U means uranium, the initial momentum of uranium is equal to 0. The final momentum of thorium and helium nuclei will be 0, because here uranium nucleus decays at a rate into nuclei of thorium and helium. So the initial momentum of uranium is equal to 0. The final momentum of thorium and helium nuclei will also be 0. That's why the both momentum of thorium and helium are equal. That is P thorium is equal to P helium. Now according to the kinetic energy formula, that is P square upon 2m. That is kinetic energy of thorium is equal to P square Th upon 2m Th, and kinetic energy of helium is equal to P square P He square upon 2m He. That is Pth is nothing but the momentum of thorium, and Ph is momentum of helium, and M.TECH is the mass of thorium, and MH is the mass of helium. Now taking the ratio of these two equations, that is kinetic energy of thorium divided by kinetic energy of helium, it comes out to be, that is kinetic energy of thorium is inversely proportional to 1 upon M.TECH, and kinetic energy of helium is inversely proportional to 1 upon MHE. Kinetic energy inversely proportional to mass. That's why the kinetic energy of thorium divided by helium is equal to mass of helium divided by mass of thorium. So based on this relation of kinetic energy versus MHE, or mass of helium and thorium, that the mass of helium is less than that of the mass of thorium. That's why the kinetic energy of helium is more or greater than that of the thorium. Because the mass of helium, the helium nuclei is lighter as compared to thorium. That's why the kinetic energy of helium is more or greater than that of thorium. So option number B is correct, that helium nucleus has a more kinetic energy than thorium nucleus, because helium nucleus is lighter in weight as compared to thorium nucleus.